We are starting now. Hello, everyone. Thank you for joining us at DataCon LA 2020. Welcome to Complex Data Transformation Made Easy with Nikita Ogivetsky. I'm sorry if I butchered that name. Before we start, there is several housekeeping things that I'd like to let you guys know. All participants are muted to avoid distractions during session. However, please use the chat app within your Wolva app on mobile device or desktop when you have comments during session. And next to the chat is the session Q&A, which will be dedicated section for questions for your speakers. We will be monitoring it and help you ensure that they are delivered to your speakers to be addressed. Please note that the Zoom Q&A won't be monitored as well, so please use the Wolva platform chat and Q&A. The Wolva app also provides you with the ability to create discussion topic on the community section that will be viewable to DataCon LA 2020 attendees on the Wolva platform. Nikita is a VP Product Engineer at Xcalar. Is that how you pronounce it?
Yes, that was excellent.
Great. He specializes in delivering complex analytics solutions for Fortune 500 companies and leads data engineering, user experience, and product management. Prior to Xcalar, Nikita earned advanced degrees in physics and math and has over 2 decades of experience in both leading and building advanced analytics systems at Morgan Stanley, Deutsche Bank, Goldman Sachs, JP Morgan, and many other leading financial service firms. Without further ado, please, Nikita, welcome, and you can start with your panel. Thank you.
Thank you very much. So, hi, folks. My name is Nikita Ogivetsky. I am the VP of Product Engineering at Xcalar. My team works with our clients to develop solutions and applications using Xcalar. You might have already heard a presentation from my colleagues, Rebecca Yi and Karun Bakshi. Today, I want to talk about my own engineering experience developing complex data compute applications with Xcalar. I will go over 2 real-life case studies. A little introduction. Before joining Xcalar 3 years ago, I spent most of my life at Wall Street building and managing data and analytics platforms at firms such as Morgan Stanley, Deutsche Bank, Goldman Sachs, JP Morgan, and a few others. It was an exciting journey. Lots of innovations, actually. For some of my work, I was granted patents. However, as vendor landscape matured, more and more of the work related to data analytics involved mostly integration of various vendor tools. Here came frustration with tunnel vision exhibited by most of the vendors I ran into as part of my role. When I met Xcalar founders in 2017, I was blown away by the simplicity and elegance of their vision and joined the company to help move this vision forward. So now, move to the next slide. So the vision was accelerate development and operationalization of cloud-scale data applications with unprecedented simplicity, speed, and scale. So firstly, what is a data application? Some of you may still remember the 90s. Remember the application server tier that was above Oracles and Teradata's and other databases? Xcalar is that application tier. Xcalar is that compute layer that makes it easy to build data applications with combination of code and SQL. Today, Python is the most supported data programming language on Xcalar. Java and Xcalar also support it in the next release. Today, most data warehouses do not have this capability unless you're doing some proprietary PL SQL work. This just doesn't exist, guys. You need to bounce your data above snowflakes, above Kafka, above S3s, etc. And this is where we come in. Customers use Xcalar to replace Xcalar in the field in this place. And I will describe this use case later today. So Xcalar decided to support Spark SQL, which is on SQL 11 compliant. This makes it easy for all the Spark developers who are like me, tired of writing the low-level code, dealing with data sets and data frames and executors and threads and whatnot. If you like to do this, sure, great. But if not, Xcalar is what will make your life easier and will let you write enterprise-grade data applications without focusing on all that low-level stuff. Xcalar gives you the ability to write code on the top of the aggregate confluence of cloud data sources and streams, test it, and immediately operationalize your business logic or ML model. Look, whether it's a data transformation, or it is a decision support system workload, or it is a data mining or something else, then you need to do this with code. And it is where Xcalar comes in. If you're looking for a system of records, Xcalar may not be the place. Xcalar is very complementary to Snowflake, to Kafka, to S3, to HDFS, and other types of cloud data warehouses, and data lakes, and data streams. When Xcalar connects to an executable data source like Snowflake, it is going to push filters and predicates. Predicates are known to work. Basically, you do not want to pull terabytes of data if you only need gigabytes or less. Xcalar is going to push down a few lines of code to make sure that you only get back the filtered rows and columns of interest, only those rows and columns that your data application needs for its compute. So the diagram here shows the high-level Xcalar application. Data can come from anywhere, from data lakes such as GFS, S3, Azure Blobs, etc., or RDBMS systems such as Snowflake, Oracle, Teradata, SQL Server, etc., or CDC streams such as Kafka, and so forth. And it can land anywhere, such as data lakes, again, RDBMS or Kafka. Data can also stay in Xcalar if you want, and can be accessed via business intelligence tools such as Tableau, Qlik, or Looker, or data science tools, or ad hoc SQL queries, or various Python IDEs such as Jupyter. Xcalar internal architecture deserves its own hour or more, and we will not go into it today, but please do contact me now during the session so that we can schedule a session later on. So to me, Xcalar problem statement was simple. The world needs a modern cloud-scale data compute platform such that a data analyst or an engineer with clear understanding of business requirements and algorithmic logic could just do it. I'm just really a just do it person, folks. So just do it without the need for deep expertise in networking, system engineering, and internals of Spark or other distributed applications and application platforms and APIs. So the goal of a data application is to consume data from one or more particular systems of record or streaming data systems where data resides, and to deliver data to another system. So you basically build data applications around data and not the other way around. Building a data warehouse around each application just doesn't scale in the modern age. So Xcalar is that modern cloud-scale, cloud-native platform to build data applications. It is designed for goal-oriented data engineers, those who would rather lose their sleep because of some business logic challenges and not because of some quirky infrastructure problems in addition to that. Moreover, Xcalar is a low-code system, unlike other tools out there. Spark is not low-code. By the way, this is an unfair advantage. Take it or leave it. Take it or leave it, folks. Basically, if you want to deal with data frames, data sets, RDDs, tuples, executors, all that stuff, there is a place for it. Then you should use Spark. If you want to deal with pure business logic and languages such as Python, Scala, Java, and Spark SQL on a more reliable enterprise-grade platform, armed with a super intuitive visual IDE, there is Xcalar. With Xcalar, SQL and Python are enough to build cloud-scale enterprise data applications. Xcalar enables the fastest dev to test operationalization cycles. Continuous integration and deployment is at the heart of Xcalar IDE. Zero changes actually required for production deployments. Some call it a DBT for enterprise, actually. So basically, Xcalar allows you to run data applications at any scales, and specifically at cloud scale. In today's presentation, I will tell you how Xcalar improved dev productivity, reduced time to market, and optimize production performance SLA while reducing TCO, total cost of ownership, for one of our customers. Besides superior performance, Scalar's other differentiator is the IDE. Xcalar created the industry's first IDE for data applications. Our customers certify that it yields at least 5x dev productivity improvement. It features declarative programming paradigm and iterative imperative programming with eager execution. Xcalar enables visual analysis, monitoring, and debug for every operation. You will get immediate feedback and high confidence production results as you're developing. Xcalar allows you to work not only with samples, but with your entire data sets, terabytes and beyond. So SQL plus visual design plus Python are the three pillars of the Xcalar IDE. To summarize, Xcalar is a low code. It turns cloud scale challenges into routine, enabling engineers to focus on the business requirements at hand rather than again and again master low-level SDKs and APIs to ensure scaling and distribution of compute operations. In Xcalar, all code scales naturally. Goal-oriented engineers just need to know SQL and some Python. The rest of the logic and the data model itself will weave naturally with the help of the intuitive low-code Xcalar IDE and, of course, engineers' analytical mindsets, which is the most important in this case. So now to the main topic of today's presentation. To set the context, our Xcalar team just finished productionalization of a near real-time streaming data compute platform at one of the top financial institutions. The wealth management division of this bank provides its customers with consolidated financial information, portfolio analysis, and mark-to-market valuations across all the investments. This data includes balances, historical account statements, client holdings, tax loads, gains and losses, and other details. The information changes frequently due to new trading transactions and corporate actions, and it may as well go several years back in history when delayed legal case resolution take place. This all results in massive data that needs to be processed on a periodic basis. So with prior Spark implementation, the bank was limited to daily frequency of batches because of very slow performance. Over 4.5 hours for a single batch. Near real-time with such a SLA, near real-time day computations were out of question. They had high dependency on scarce expert programmers. Engineers were expected to understand Spark internals, have Java expertise, and be savvy in the business domain. Very hard to find combination of talents. 25,000 lines of monolithic Java Spark code created a job security minefield. Consequently, an unacceptably long time to value, long development and troubleshooting cycles. Last revision took 2 people over 3 months to refactor. 6-person month to just refactor. You can imagine the effort that a new such project would require. There was no developer IDE for distributed data applications, just Java editor with zero transparency and debuggability of the underlying data. All of this contributed to a very high total cost of ownership. So here comes Xcalar. Banks, engineers, and managers fall in love with Xcalar IDE. With Xcalar, they replaced 25,000 lines of obtuse, here again, speaking of job security, Java Spark code with over a dozen visually transparent scalar modules. Engineers need to know only SQL and a little bit of Python to become dangerous and create powerful compute applications. Xcalar unlocked time to value for new capabilities, so new business requirements do not need to wait 3 to 6 months to be implemented. Now development and testing takes just days, maximum weeks. Xcalar is low code. No need to develop distributed compute. All tasks related to scaling, indexing, distribution, and orchestration are taken care of by the Xcalar engine. Batches that took 4.5 hours in Spark now run only 15 minutes in Xcalar over the same infrastructure, more than 10x performance boost. This eventually enabled the bank to implement near real-time updates for their customers. Now, the customers do not need to wait until tomorrow to see updates to their portfolios. They will see them almost immediately. In today's Xcalar streaming compute platform, implemented in Xcalar, the data for dozens of data applications is fed both from HDFS data lake and from several dozens multi-partitioned Kafka streams. So on the screen here, you see kind of the inputs in the current implementation of the streaming platform, with the data lake sourcing the base data sets, and then obviously all the updates come through a multi-partition, multi-broker, multi-topic, etc. Kafka streams. And then they go through a set of transformation pipelines that we'll look into later, and eventually it goes back into Kafka. And from Kafka, it's distributed to other downstream systems. So our customer estimates that Xcalar enabled 5x developer productivity and overall 20x improvement in time to market, given obsoleted need to redevelop distributed compute and shorten operationalization on troubleshooting phases. 10x total cost of ownership reduction and performance boost, and improvements in their productivity and in time to value were the key winning factors for our customer in this case. I imagine that many of you, like me, are in love with business logic, business algorithms, and SQL. But how many of you are in love with RDDs, datasets, partitioning, executors, and tuples of Spark and other low-level SDK and API, fighting infrastructure and performance optimization issues at the cost of programming business logic? I'm an engineer, if I'm an engineer just out of school and I want to put Spark on my resume, I would love to do that. But this is not the future for data engineering work. For data science, maybe, if you want to work with SDKs and APIs and write batch programs, of course, you should stay with Spark. It is a tool for you. If you want to free yourself from low-level minutia and focus on business logic and use the enterprise-grade system that is guaranteed to outperform Spark, try out Xcalar. When I was leading 50-people teams at Morgan Stanley and Goldman Sachs, the instrumentation overload required to write and maintain data applications was really bogging down the efficiency of my team. That was a real problem for me. With Xcalar, that part is gone. Engineers now are empowered to work on business logic without looking back. I no longer have to worry about infrastructure issues and skyrocketing costs due to unoptimized configurations or wrong indexes, but instead focus on the business logic around my fraud detection, anti-money laundering, marking to market, and other real business requirements. So while that is the core use case that I would like to present one day, it would require the whole day to cover all details. Today, I want to exemplify the power of Xcalar programming paradigm and Xcalar IDE by zooming into one of the side data applications that we had developed while working with a customer to implement the strategic streaming platform powered by Xcalar. As mentioned earlier, the bank streaming platform integrates dozens of regional compute-heavy Xcalar data applications that continuously process over 2 terabytes of data from HDFS and with several gigabytes daily volume of live updates via multi-partition Kafka streams. Each of these data applications performs complex computes over more than 30 source tables and microbatch increments in near real time and outputs compute results back into Kafka. You can imagine the complexity. A complex system like that requires a high level of transparency to analyze its internals and identify volume and performance trends and correlations, and discover, of course, opportunities to improve and catch any bottlenecks before they become problems. For this project, I want to pull a bunch of logs, such as Apache logs, Linux logs, Scalar logs, and I just want to do some log processing. What are my next steps? So I love SQL and I hate parsers. In this presentation, I will show you how I leverage Xcalar Data Application Platform to extract rich semantics of operationalized metrics of the Xcalar streaming platform and publish it as a Data Mart with just SQL, embellished with some Python and the data model weaved together using just Xcalar Low Load visual programming. So as mentioned, the main input into this Data Mart is the streaming platform application logs, including information about initial sources, Kafka streams, application configurations and metadata, application regions, sources and dependencies, batches and batch versions, micro-batch versions, processing stages and microservices such as load, ingest, insert, modify, delete, execute, export, snapshot, recovery, etc. Live table life cycles, macros such as the row counts of increments and sizes and versions of tables and table deltas, transactions and their metadata, and of course errors and warnings, if any. So how do I do this? I decided to use the Saas version of Xcalar that is available at myxcalar.com, and actually everyone can go there and register for a free account. And this slide shows the Saas version of Xcalar that I use to perform this analysis. As you see, you can get started with just a few easy steps. First, register at my.xcalar.cloud. And of course, everyone, please, you can go and try it out. Then log in, start your instance, and eventually load data to start a new project if you already have data and connections created. As with every data compute application, we need to start with data. As shown on this slide, I updated my application, I uploaded my application logs into S3, and then loaded them as a single column CSV files. First, I navigated to S3 bucket. Some data is already there, but some I can add right here. I uploaded my log file, and selected it, and selected a single column CSV format as input. Now going to step 2, I reviewed the auto-detected schema, which was pretty basic in this case because I just ingest every row as a single column. And eventually I loaded the table and navigated to my notebook project. In this case study, I would like to highlight a few awesome capabilities of Xcalar that made my data engineering experience pleasant and efficient. The first awesome capability that I want to highlight is that I did not have to create and deploy a predefined log parser. Rather than parsing log files on ingest, I loaded them into Xcalar as a single column CSV, as we just showed in the previous step. And this is shown here in the first step of this diagram. Then I developed a simple custom scalar function in Python that applies a basic regular expression to extract syntactic components of log records. Scalar functions in Xcalar provide a powerful way to extend built-in SQL operators. Traditionally, scalar functions are known to work on tuples or one or more parameters and give you back a scalar value. This is also what our scalar functions do in Xcalar. You can point them to columns from one or more tables, and they will give you a value that you can put into a table, any table. Scalar functions execute on one row at a time. They run across all CPUs in the cluster and compute across all rows in parallel. And that's the most powerful feature of the Scalar functions. It boosts performance proportionally to the number of CPUs that your cluster has. For example, if your cluster has 32 CPUs across all nodes, performance is boosted 32 times. If you have 144 CPUs, it is boosted 144 times. 1,000 CPUs, 1,000 times. With Scalar, I could develop it interactively and test iteratively. Of course, a similar performance boost would apply if I run Scalar function that applies a machine learning or natural language processing algorithm in Scala. But this topic deserves the whole other session. Please contact me if you're interested in that topic. You can see the application of my Scalar function in the second step of this diagram. The function is very basic. It has just pretty much 9 lines of code, and there's some Python import statements on the top. And it basically what this code does is basically defines a regex pattern, and then it applies. That's it. Next step, and then this function is applied in parallel, leveraging all CPUs and cores in my cluster. Next step, I extracted syntactical attributes, then extracted semantics such as parent-child relationship between records and grouping records by applications, that is distributed data applications, microbatches, and processing stages. And lastly, I published my temporary table interface that other modules can reuse. Wow, guys, all this was just SQL. Isn't that amazing? So the second awesomeness of Xcalar that I want to highlight is the power it gave me to combine declarative and imperative programming paradigms. The thing is, when you start developing a data mart, you may not yet know what the final data model will look like until you have loaded and profiled the source data and analyzed its patterns. This is a kind of catch-22. Xcalar allows you to break this evil circle. It empowers you to, it empowers the result-driven data engineers who understand the business goal of what they're doing. Scalar programming paradigm allows them to work iteratively, fine-tuning the solution and the data model, developing and testing continuously, one bit at a time. As you see in this diagram, analyze block in the middle, once I finish parsing the data, I'm able to start analyzing the data attributes using profiling. You see this kind of, I can do the profiling and correlation between columns, and SQL, I'm analyzing the data with SQL. Then I build the first set of business logic here, and interpolations using SQL, interactive modules, and extending it with SQL with scalar functions and table functions, which we'll speak about later. And then more analysis and testing, and then more development of business logic, and so forth. And so on, until I arrived with the final data mart, with a data model ready to be shared with BI developers. This slide illustrates how I eventually organized my Xcalar data application and refactored it into 3 application modules. Module 1, log parsing. As discussed in the previous slide, here we load source files, parse out log syntax, collate stack traces. Remember that stack traces span over multiple lines, which need to be associated with the first complete log entry, kind of the parent-child relationship, and mainly extract workflow semantics related to streaming applications and their component state changes, microbatches, identifiers, and processing stages. Notice how here I can track intermediate table row counts, skews, and time taken. See these little numbers on the top after each step while developing my data application. This lets me preview and adjust my data flow iteratively and interactively. When that's done, we move to module 2. Data preparation. Here we extrapolate application state changes and microbatch identifiers and enrich the corresponding data records that were logged by the same Xcalar application. Thankfully, SQL gives us very easy ways to do that. The awesomeness of Xcalar that allowed me to combine the declarative power of SQL with the imperative programming in Python made this task very easy. Now we move to module 3. Compute and build normalized tables. With the main measures and dimensions computed, I now focus on the final steps. I exploited objects written into log files as JSON blobs into their own data structures to enable tracking size, row counts, and other properties of the live tables of each data application over their lifetime. I will drill into this in more details in the next slide. Lastly, I prepared the final tables, the data mart, the data cube in portion of my data mart, and finalized the data model. So this last computation in this tiny data applications that created the data cube, it was done with this with one of the SQL modules that I exemplified, kind of showing you the types of SQL statements that can be used in Scalar. So in modules 3 of the previous slide, I mentioned the explosion of JSON objects containing microbatch sizes and row counts of each of the substreams into a separate normalized table. For this, I developed a reusable table function, which I will explain here. A table function is a phenomenal construct in Scalar that lets me generalize a group of operations that manipulate and retrieve data from one or more input tables and returns the result set in another table. And I can generalize it as a function. I then can use this function in the from clauses of my SQL statements. So where a scalar function extends the kind of the select types of functions in SQL statement, the table function extends the from what I can use in the from statements. Look at the SQL node in the middle. Read this one. It's select from the get increments table function. This is the very basic select statement here, consisting, and this table function was built out of 3 elements that are shown here in the middle. So, first, the first element explodes an array of JSON dictionaries into rows, then extracts and normalizes attributes, like, for example, increment sizes, microbatch increment sizes, and row counts of all table deltas that were part of each of the microbatches. And then and in the last step, I basically filter the result set to get rid of extraneous details and keep only information about the user, the tables that are relevant for the user created tables. So this table function and then applied from within SQL statements. Because table functions are reusable, I was able to leverage this table function in another data flow. This slide shows a personalized data application. Here you see how dozens of SQL operators that I developed interactively in the previous slide got compiled down to hundreds of execution primitives. The callouts show zoomed in set of operators, as you can see here. Using this view of the execution plan, you can track how data was transformed alongside the execution path. The row counts, if you zoom into this stuff, you see the row counts, the skew, the table skew in which is very important in a large in the many nodes cluster, and the time taken by each of the execution primitives. These execution primitives, such as filters, maps, joins, etc., are compiled down from the high-level SQL statements. This lets you troubleshoot your application and identify opportunities for improvement. This operationalized application can now be either scheduled or invoked as a microservice via Xcalar shell distributed along with Scalar. Finally, the data model is exposed to BI developers. Scalar supports Tableau, Qlik, Looker, and other BI tools. Here, we decided to use Jupyter Notebook to execute SQL queries against scaled Data Mart and build visualizations with Matplotlib, Seaborn, and Seaborn. In this case, Jupyter Notebook extracted data from Scalar using PyODBC and Spark SQL connector. So that's the last slide, folks, and it's that's the review of what we've done. The real value for me as a data engineer was that I was able to build this data mart within its data model interactively and iteratively while I was analyzing data and developing business logic at the same time. No advanced DDL was required whatsoever. I did not need to pre-create indexes, aggregates, or metadata. Scalar implicitly creates this for me on the fly based on the data. I was empowered to work on this in a highly parallel fashion without any knowledge of iterators. No niche expertise such as Java, Scala, multi-threading was required, just SQL and some basic Python. Scalar is low code. Scalar engine took care of the rest. Xcalar SQL scalar functions, which are really the modernized stored procedures, work on all rows in parallel, enabling superior performance on full data sets rather than sample data. With scalar functions, I can write Python code and I can do it all this myself here and now, and that is the power to the developer. SQL is the king, and that's great. And look what we've done here. We built a whole parser in SQL because I got regular expressions and I got the ability to invoke functions in parallel using all CPUs in my cluster. Moreover, for all joins and unions and group bys, for all operations in Scala, I can utilize all resources available on the backend without even worrying about it, because I work serverless within the confines of my IDE. Scala will ensure maximum resource utilization for my queries and data applications. Is that cool or what, folks? I can take a very complex data application and step through the whole code down to execution primitives on a production-like data behind. That means that in production, it will work exactly as it worked in the lab. And this level of CI/CD is a game changer. Users can work with entire data sets. If you made a mistake, you can go back and amend interactively and iteratively. Every stage of my SQL query becomes a data flow graph that I can debug and analyze and see exactly what's happening. Many of our customers use Scalar as a compute layer on top of Kafka, S3, Snowflake, and other databases, and they are replacing Spark in this place. Scalar gives me a pure compute layer. I mainly deal with code, and I am happy to have the power of SQL available to me. And yes, we're using Spark SQL because Spark SQL uses ANSI 11, and we are able to extend it beyond its existing capabilities into regular expressions or any other Python libraries, such as TensorFlow, NLTK, and so forth. So this concludes this use case stories description. Now we can take some questions if we still have time.
Hi, yes, there is only one question. Can you explain how scalar different than vector?
Then what?
Vector?
Vector. I'm not sure what vector means. Oh, how scalar mean different from vector? Oh,
yes.
Just not scalar, but scalar. Scalar is something that returns you a single value, and the vector will return you an array of values, basically, right? And then you have matrices and so forth, and then you get tensors. Does that answer the question?
Yes. I don't know if anybody else is interested in any questions. I don't see any other questions right now. I guess we can close this session for now. Do you have any other anything else to say, Nikita?
Well, if no other questions, then please reach out if you're interested to learn more.
Definitely. Okay. And thank you, Nikita, for your presentation. And I appreciate all the attendees for questions and interactions during the session. Please contact the speaker if you have any further questions regarding this topic. Please provide your comments and feedback to us or the organizers on community board, or start discussion there to connect with others in the DataCon LA 2020 community. Thank you for joining today's presentation. I hope you can gain some insights from the session. Have a wonderful day, and thank you for being part of this year's DataCon LA. Thank you so much, Nikita. Be safe and be healthy. Thank you.
Thank you very much. Thank you for hosting, and thank you for attending this session.
Definitely. Have a good day.
Have a good day.